Well, good afternoon, everyone, and welcome to this Wetsus webinar on artificial intelligence in water technology. Before I will introduce ourselves and also the speakers, let me just start with a short introduction into the subject. As you know, nowadays, large amount of data are collected. For instance, from social media, we have large amount of data in terms of videos, tables, text, mention it. Also, we have lots of data available through the CCTV systems in our cities, but also the cameras near highways, but also in water infrastructures. Yeah, more and more data are collected through sensors. And nowadays, the management of the water infrastructures benefit so much from the collection, the automated and novel collection of the data, and also the processing of the data, and the transformation of this data into information. And you can think about the predictions of malfunctionings. Well, in this webinar, we will learn more about some other examples and dig deeper into this fascinating world of AI in water technology. So let me start now with the introduction of ourselves. My name is Karel Keesman. I'm a personal professor in the Mathematical and Statistical Methods group in Wageningen, in system theory. And here's Dukle Intema, co-chairing this session, and he's a scientific program manager at Wetsus. And he will also keep an eye on the chat functions. So please use the chats so that we can collect these and we can come back to that later on. The program. First of all, we have 3 presentations of 20 minutes each, followed by 5 minutes for, let's say, the general discussions, specifically for this presentation. Yeah, so you can ask questions, technical questions, things that aren't clear, only for 5 minutes. Then, after the 3 presentations, then we have something like 25 to 30 minutes left, and that's for a general discussion. So if you have general points for the discussion, also use your chat function, or you can use your microphone if you wish. So I think that that's the program. And then it's time to introduce the first speaker, and the first speaker is Professor Dr. Ingenieur Peter Baltes from the TU Eindhoven. And Peter is currently full professor and chair of the Mixed Signal Microelectronics Group in the Department of Electrical Engineering in Eindhoven. He received his master's degree in '85, also in electrical engineering at the TUE. Finished his PhD project in 2004. And in between, he was appointed at Philips, but also at NXP for some 22 years. And his key areas of expertise is high frequency, integrated circuit and system design. Well, the title of his talk for this afternoon is Inspecting Pipelines Using Swarms of Evolving Sensor Spheres. So Peter, I would say the floor is yours, but it's your turn.
Thank you.
Please go ahead.
Thank you very much, Professor Keesman. I really appreciate the opportunity to tell a little bit about one of my favorite projects here. So thank you very much for the invitation and for this opportunity. Ladies and gentlemen, what I'm going to talk about is a project that we have been working on since 2015, where we looked at technologies for solving a class of rather generic problems. And these problems have to do with exploring unknown environments. So you can think about many centuries ago when people explored the world, tried to make a map of the world and try to find out what was in places far away. And they did that by boat, or they did that by horses. But whatever means they took and chose to explore this world, they always had this problem that they had only a limited amount of stuff they could take with them. And that was a problem because since they didn't know exactly where they were going, they also could not predict accurately what they would be needing there. And of course, that's centuries ago. So we have to go a little bit beyond what people did in those days, right? They would go to stores like this. But even in modern times and your own experience, you might have similar encounters. For example, if you go on vacation, you also sometimes go to places where you haven't been before. And you also have limited amount of stuff that you can take with you. And you also have this problem that you don't know exactly what you will need, what kind of clothing, what kind of food, and so on. And so there's also way too much to choose from things that you could potentially bring, much more than you can fit in your car or whatever means of transportation. And again, there you have this problem that you're going to explore, you're going to a place that you don't know, and you don't exactly know how to prepare for that. And this problem comes back in many applications. And it's a difficult to solve problem because it's of the class of chicken and egg problems. Right? It's if you would know the place that you are going to visit, that you are going to explore, then it would be easy to decide what you need. But to explore that place successfully, you need to bring the right stuff. So we need to get out of this chicken and egg cycle to come to a solution. And since there was more than just these two examples, for example, you can think about exploring, let's say, a nuclear reactor. If something goes wrong, it would be really nice to be able to see what's going on in there. But you could also think about, for example, if you have in healthcare, if you have a patient, you might want to look inside that patient and see what's going on in there, and you don't know what you're going to encounter. Or closer to home, you might have pipes buried below the ground, and you want to see what's going on in there. And in all these cases, the essence is that you don't know exactly what you're going to encounter. And so you can't exactly define the optimum sensors for observing such an environment. So what do you do at the university in those cases? Well, you start a project, right? It's difficult, it's generic, it applies to a lot of problems. If you can solve it, then it's very likely to be useful. So we set up a project called the Phoenix Project to address this class of problems. And of course, we didn't do that alone. We worked together with a number of other organizations that you see listed along the top. And of course, this costs a lot of money. So we are very glad that the European Union funded this research for the full 4 years. And we are very appreciative of that. So when we started this project and we got together to write a proposal, it was obvious that if you want to explore something, you need to bring a sensor into this environment. And so conceptually, there's this sensor. It can be a sphere or whatever. There's some electronics in there, some sensors. And we put it in the environment, and then later we extract it and we measure what we extract the data from the sensor, and we can find the measurements, we can obtain the data that has been observed in this environment. The problem, of course, is that you need to know upfront how often does such a sensor need to log its data. How many of these sensors do you need? How big can this sensor be, right? For example, if you're going to explore and you suspect that there might be some blockage of a pipe, then you probably want the sensor to fit through. But if you don't know how big the blockage is, how much space is left, then how big can the sensor be? How expensive can it be? How heavy can it be? How accurate should the measurements be? What are you going to sense in the first place? Is it pressure? Is it temperature? Is it location? Is it acceleration? How long does such a sensor need to be in the system? And therefore, how long should the battery last? There are many of these questions. And again, it comes back to the same chicken and egg problem. If you know what's going on down there in the pipes, or inside a person, or inside a nuclear reactor, or whatever your problem is, then you can make a very good choice in these parameters. But if you don't know that, and by definition you don't know that, because otherwise there would be no need to explore, then this is a fundamental problem. And one of the first things that you need to choose is which direction are you going to go? Are you going to make one super sensor that can do everything? Or are you going to go to a swarm, a collection of smaller sensors? The super sensor has definite advantages. You can make very high quality sensors, you can have very large memories, you can have a large battery, but still it will be limited. Wherever you go, there's always a size limit. If it's in the pipe, then it better has to fit in the pipe, and even through a blockage. If it has to go in a patient, then the patient preferably should be able to swallow it without too much trouble. And so there's a size limit. And therefore, if you want to have a generic solution, it's nicer if you have a technology that allows you to make things small, because if you can make these sensors small, then you're much more flexible, you can address many more problems, and you can solve the fact that these smaller sensors have more limitations in battery and sensors and so on by just having more of them. And in many applications, it's easier to fit 10 small sensors than one really big one. So that's the research direction we chose. But still, even if you have many small ones, you still need to choose how big are they, how often do they need to measure, and so on. You still need to make these decisions, and you're still stuck in this chicken and egg problem. So how are we going to address that? Well, a very simple way, very engineering approach would be just try it, right? You take some sensors, you put some common sense choices in these parameters based on hopefully discussions with an expert that can give you some guidance. And then you just configure them, you put them in the system. Somewhat later, you retrieve them, you get out the data, you find your observations. And if they're not quite right, if that's not exactly what you are looking for, you iterate. You just try again and again and again. And at some point, hopefully, you're going to be successful. And of course, you can be smarter, right? In this example, we take a swarm of sensors, but in fact, you could have sensors that are not the same. We call that casts. So you can have, for example, a swarm of sensors that consists of specialized sensors, some that are good at storing a lot of data, some that are good at very high resolution temperature measurement and so on. And that allows you some better trade-offs, but also gives you even more parameters to choose. So this choosing of parameters is still an issue, and very quickly it becomes a lot of work. In this iteration, trying again and again, putting the things in there, getting them out, reading them out. First time it's fun, the second time it's still interesting, the third time it becomes routine, and the fourth time you start hoping that you can find a student to do it for you. So what do we do in that case? Well, what if we could do this optimization of the settings in a software environment? What if we could have an environment that would allow us to predict, to simulate what would happen and find the optimum settings of the sensor? That would help us, right? Because then you can make an optimization algorithm. There's many algorithms to do that. And you could immediately get the answer for the optimum sensor. Of course, that only works if that simulated environment is accurate, if it has a model of this unknown environment, and you don't have that. So instead, what we did is we have a series of environmental models, a number of hypotheses. The environment could look like this, or like that, or like that. And then you can simulate and see how these sensors would fare in these different hypothesized environments. But then you still don't know, right? Because you have now a number of answers, and you might find that some sensors are more often useful than others, but you still don't know for sure. So the last step we did is to intermix these two. We first do a common sense guess for the environment, and we optimize in the simulation the sensors. Then when they're optimized, we configure them and put them in the real environment. So we first go through this loop and optimize the sensors in software. Then when they're completely configured in software, we configure them in hardware, and we make them go through reality. So we put them in the system, we get them out, we read them out. And then something interesting happens, because then we have data from the real world, and we can compare them to the data that we had on our models, on the collection of models of that we thought could describe this environment. And we can see which data matches which model most accurately. And the way you can do that, and the way in which we experimented with that, is to do that using genetic programming. So we have a collection of models that we consider as a population, and we have this population compete on matching the measurement data as accurately as possible. And then the ones that do best, we combine their properties, make new models, and run them again through the simulation loop until we converge to a limited set of hypotheses that each describe the measurement data accurately. And then we use these models in the second step in the simulator to optimize the sensor models, the virtual sensors, for these more likely models of reality. And again, when we have then the best possible models, we make a second round through reality. And this ratio, the number of times we go through a simulation loop and the number of times we go through reality, in practice can be quite large. Think about maybe 1,000 iterations in software versus 1 iteration in reality. So this is something that we tried, and that actually works for a number of realistic problems. So we started working on that, and then of course we needed these sensors, and we needed these sensors to be flexible. And at the same time, they needed to be resource limited, right? We had this swarm of small sensors. So what we did was we made a sensor that has some configurable generic input for different sensors that we can add to it. It has data compression and processing and memory to store the data. And it has a transmitter and receiver to communicate with other sensors. And that's something I didn't mention yet. For a long time, we had discussions whether we should have communication at all, because communication essentially costs energy and we don't have much battery. And we found that many of these communication problems we can do later on. We can, once we have retrieved the data, we can combine it, and we don't necessarily need to exchange data between the sensors. But there's 2 exceptions. One is that we want to know where the sensors are, because measuring sensor data is interesting, but mostly if you know where it has been measured. And to measure that, we need to know where a sensor is, and we use communication for that. There's a research area for that one of our colleagues in this project worked on, where you reconstruct the location of the sensors by measuring many times the distances between pairs of sensors. And that's what this transmitter and receiver are for. So this is what we built. This is what it looks like in reality. This is not miniaturized yet. It looks about this size. This is a typical sensor, so it's 50 millimeters diameter. And of course, when you have students make these things, then they might also look like this, or even like this. But the idea stays the same. We have a configurable amount of electronics with a battery and a waterproof shell. And then you need to try that. So we also built a setup like this in the lab, so that we had a place where we could conveniently do very simple experiments, where we also could observe what was going on with the pipes. And we ran many simulations with that. And just to give you an idea what that looks like, if you look at my background, rather than the slides for a moment, you can see the students at work with this setup. And you can see that they have a lot of fun. It's not a bad chore for them, not a punishment. And they generated a lot of new insights and a lot of new data. So what did we get from this, and where are we going now? Well, we have the technology from Phoenix. That's where we are now. So we have these sensor balls, we have the software, we can run experiments. And so there's one direction that we call Smarble, where we are going to industrialize this and commercialize this, where we're going to apply it to real current problems with the technology that we have today, the size balls. And there are applications where this is already useful. We're looking at, for example, mixing and process reactors, at sewer systems, and also at water distribution systems, where the size of this is really not a big showstopper. At the same time, and in parallel, we are continuing research and we are exploring new directions. And one is miniaturization. We really want to make things smaller so that we can also address applications that you cannot do with this. If you ask a patient to swallow this, most patients would very politely refuse. So for many applications, it has to be smaller. We also need to make improvements to localization. I'll come back to that, because that part has not been completely solved yet. And we have some dreams, like once you have sensors down there, can you also have actuators? Wouldn't it be nice if you could find a leak and not just detect it, but maybe if it's small enough, even close it, at least temporarily? Wouldn't it be nice if you found a blockage that you could maybe widen it or remove it? That's again a dream, right? At the moment, we don't have the energy to do that in the battery, but we have some crazy ideas. And we're looking at new applications. So that's where we are today. And I'm going to show you 2 more small things. One is really small. This is where we are now. So this is the electronics that has been integrated on 3 ICs. Total volume of this, well, it's less than 1 cubic millimeter now. And the energy consumption of this, where in these balls, is still in the tens of milliwatts. In this case, it's less than 1 nanowatt. So this gives you an idea of the progress we're making there that will allow us to, for example, make things that people or animals or so would want to swallow, or that you could fit in really tiny places. The other thing that we have made quite some progress on was localization. I mentioned the localization, the need for knowing where we are, and you can in many cases not do that using GPS. You need something that works in environments that are shielded, for example, from radiation from radio signals from satellites, um, like underground or inside people or in nuclear reactors or whatever. So we used ultrasound, but the problem with ultrasound we found was that in some cases it works quite well. But unfortunately, especially in pipes, we had a big problem because in pipes, there's a lot of reverberation. We see a lot of echoes. And we found almost no correlation between the time that it took for a sound to go from one sensor to the other and the actual distance. Unfortunately, we had a really smart student. He came up with a solution for that. And you can see in the rightmost graph that this chunk that you see here has been replaced by, a very accurate link between the measured distance and the actual distance. It's not perfect, but it's down to a few centimeters. So this is where we currently are. I hope it gives you some idea of what we have done and what we are going to do, and what you could do in inspecting pipe systems, for example, without having to dig them up, using advanced algorithms to optimally inspect them, even without permanently installing sensors or taking them out of production. Of course, we didn't do that by ourselves. I already mentioned the organizations. These are the people behind the organizations. We are quite thankful to all of them. They did all the work. I just am allowed to talk about it. And I can tell you, though, that we had a lot of fun doing this. That concludes my presentation. Thank you very much for your attention. Maybe I can answer some questions if there are some.
Let me first thank you, Peter, for your nice presentation. A very interesting one, where you showed the full integration of software and hardware for let's say, within an artificial intelligence context with potential applications in water technology. So there may be some questions here. Dukla, do you have some?
Yeah, there's one question coming on in, and the question is, what parameters can be measured during these sensors?
Yes, that's a really good one. So what we have done is we have, in the current one, in these ones, we have at the moment acceleration in 3 dimensions, rotation in 3 dimensions, magnetic field in 3 dimensions. We have temperature and pressure, and then the ultrasound communication. In the small ones, we went one step further, and we have a universal sensor interface, so that we can configure the sensors that we can attach to that. We can program this interface to deal with a really large variety of sensors to make it even more universal.
Thank you. And there's another question coming in. And I think personally think this is also a really interesting question, because could you elaborate on the method of ultrasonic localization?
Yes. Yeah, that's the work of Dr. Duisterwinkel, one of my colleagues, is now working with Antea, the industrial partner for Smartbots. He worked for 4 years, and he came up with the concept that if you have a large number of sensors and you measure the distance between each pair of sensors, then you can make a set of equations with as unknown the position of every sensor and as known the distance between every sensor. If you try to solve that, you find that there's no solution, right? Because the measurements are not accurate enough. And so you have an overstated problem that does not have a solution. But he found an algorithm that gives the most likely solution. And even for situations where things are a little bit more complicated, like, for example, if this whole swarm is moving and distances are changing over time, and you don't do all the measurements at the same time, then the problem becomes more complicated. But essentially, it's the same thing. So what you do then is you look at the sensor sort of as a 3-dimensional object that can bend and move through pipes. And if you have that information often enough, then you can reconstruct the location of this whole, almost, you can think about it almost like a snake, right? That goes through your pipes. And by accumulating the previous positions and the distance to the next positions, you can then make a map of the pipe. There are some things you need to do extra though. If you don't do anything extra, then there is a risk of cumulative errors. Right? You make a small error, next time you make one more error, then these errors add up. And if you're unlucky, and Mr. Murphy says that you're always unlucky, then that's not going to work in the long term. But there are things you can do. You can calibrate, for example, at the moment that you go around the corner, because if you have acceleration sensors and gyroscopes, then you can find whenever you make a corner. And that's a reference point that each of the sensors has to go through. Then there's the magnetic field. If you know the magnetic field, in some cases, that's lined up with the Earth magnetic field, and it gives you an absolute direction. So there are things that you can add to this navigation method that makes it more accurate. And that's something you need if you want to have reasonable accuracy, let's say within half a meter or so, for extended distances like kilometers. That is something that starts with doing accurate distance measurements. And we're very glad that now we have, with ultrasound, we have found a way to do that even in pipes. In some cases, that's still not good enough. And in water pipes, that would work. But for example, in sewer systems, the problem is that the speed of sound might not be constant, because you don't know exactly what is around you, what in the fluid and what objects are around you. And so the speed of sound might be affected. And we are now also working, and we have the first prototypes where we combine the ultrasonic distance measurement with magnetic distance measurement. And if we combine them, then we can do even more accurate measurements.
Thank you for your answer. I think that explains a lot. And some other questions are, do the sensors have a real-time clock? I think they have, but it can be probably
yes,
answered.
They do. It's not very good though. To make a really good clock costs energy. So you can make clocks that are accurate over the long term, but if they are low power, they have phase noise. That means they jitter, right? So go a little bit faster, go a little bit slower, and so on. So if you want to do, for example, distance measurements with ultrasound, then the time the ultrasound propagates from one sensor to the other is in a millisecond range. Your clock might well be off by a significant part of that, and so you might get very inaccurate measurements. So what we do instead is we do round trip. We transmit an ultrasonic signal from one sensor, from sensor A to sensor B, and immediately answer from sensor B to sensor A. And in both cases, we don't just transmit a pulse, but we also include the serial number of the sensor, and we include the time that each sensor has on its clock, so that we can calibrate the time differences when we retrieve all the sensor data. So it's a little bit more complicated, but we can work with not very good clocks. And if you look a little bit further into advanced algorithms, then you can improve a lot. And that's what you need, because if you go to these small sizes, then your battery necessarily is going to be very small as well.
Yeah, that's clear, I think. I think we should go to the last question before going to the next one. So one last question would be then, it sounds like complex calculations. I agree with this. So where do those calculations take place, and are they in the balls? Because I can imagine if you do a lot of calculations, then it must need a lot of power.
Yes, yeah, indeed. And so we try to do almost no calculations. We try to store mostly raw data in the memory of the sensors. And after we retrieve them, we have, of course, a larger computer, and it's connected to the mains, and we have enough power, and we can do all the calculations necessary. The only thing we do in the balls is two things. One is we do some data compression, because there's a trade-off between doing the calculations for data compression and the energy required to store data in the memory. And we try to find the optimum there. And the other is we have a Bayesian tree network that determines when to take a sample in the first place. So we can add some, but that's not software running on a general purpose computer. That's really hardwired logic that's configurable. So also very energy efficient. And it makes sure that we do the minimum amount necessary to really collect the relevant data. And that Bayesian tree is programmed again from the genetic programming, and that runs in the optimization of the simulation loop.
All right.
Thank you very much for your interesting answers.
Yeah.
We have a number of more questions, but I will save them for the discussion later on. Thanks for now.
Thank you very much.
Yes, thank you, Peter, for sharing this with us. We'll see you back during the general discussion.
Yes.
Then we can move to the second speaker, which is Dr. Engineer Mark Roest from Fortech. That's a company in Delft. And Mark is a managing partner and one of the co-founders of Fortech. And he obtained his master degree in applied physics at the TU Delft, and also a PhD degree in mathematics, applied mathematics in Delft as well. His work mainly focuses on the development of and improvement of simulation software, but recently also focused on machine learning type of techniques, which nicely fits into this context. The title of his presentation is A Small Selection of Techniques for Smart Network Management. So Mark, please go ahead.
Yes, thank you, Professor Keesman. So my name is Mark Roest and I work at Fortech. Unlike the other two speakers, I am not a researcher. So I thought it would be better if I do not try to compete with the other speakers in terms of fancy new research. And I had better stick to the more practical side of things. So I changed the title of my talk a little bit, although the content is going to be much the same. And the title of my talk is AI in Digital Twins. And I'm very much aware that these are two buzzwords. It's probably the shortest sentence that you can make with these buzzwords. But I think what I hope to do is to give you a bit more context about AI in an operational setting. And the term of digital twins is sort of an excuse for discussing that. Now, before I move to the actual content, just to give you a feeling about who we are. So Fortech is a company of 25 colleagues, and we develop software for all kinds of computational applications. And that often has to do with prediction or analysis or simulation, optimization. In fact, any software with a large computational part is where we like to operate. And what we do in practice are these kinds of services. So we develop model software. And by that, I mean the traditional kind of models, so equation-based models. That is where we started some 25 years ago. For a long time, we've also been working on combining sensor data or data in general with computational models. And the story there is that a model can be used to compute anything, but you never know if it's related to reality. And the data is, of course, a real thing, but you only have it in certain places and at certain moments. And by combining the two, you can get a more complete picture of whatever it is you're doing. And then I would say some 5-6 years ago, machine learning came also into our package. And it says here machine learning engineering. And that's on purpose because machine learning is only part of an actual system. I will talk a lot about this later on. But machine learning engineering also involves the data processing, feature engineering, maintenance of machine learning algorithms, and stuff like that. Then we do a lot of, excuse me, a lot of data engineering, which means from the raw sensor data, turning it into data that you can actually use for applications. There's always also some dashboard involved in the kind of systems that we do. And because we are more or less on the high end of technology, a lot of the things that we do also involve consultancy. Now, we have been doing these services, as I said, for some 25 years now. And then a couple of years ago, the concept of a digital twin came up. And we noticed that everything that we had been doing until that point was sort of related to that concept. So I think that's a very nice thing to discuss. What is digital twin and how does all this work fit in there? And I will then focus on the machine learning AI part. Now, there's a lot of confusion about what a digital twin is. Perhaps some of you hear this for the first time, but I think most of you will have heard it before. And I think if you ask 10 people what a digital twin is, you'll get 10 different answers. And a month ago or so, I found this definition by a market research firm, Juniper, which I think is a very good definition. Most of the time, I don't have that much respect for market research firms, but these guys or girls did a wonderful job. So I'll read the definition, and then I'll highlight a couple of things here. A digital twin is a virtual model representation of a connected physical product, a process, or a service across the whole life cycle, design, build, and operate. And it uses operational real-time data and other sources of information to enable detection of issues, to do learning and understanding, and to test and simulate scenarios in the physical model counterpart. Wow, that's quite a definition. Things that I would like to highlight is in the first sentence, it can be about a physical product, a turbine, or well, whatever, a machine. But it can also be about a process, or it can be about a service. And the second thing to notice is that it's in the whole life cycle. So a digital twin starts in the design phase when you are designing your system or your products or whatever. There you start collecting the first amount of information, which is then the design drawings and the specifications. Then it lives through the build phase where you develop and build the asset. And again, you collect information there, all kinds of information that is collected during the building. And then it moves through the operation, where you get the operational sensor data. And all this data together, design, build, and operational sensor data, comprises the digital twin. And then there are a couple of use cases in this definition. So the first is detection of issues. I'll give you an example later on. The second is learning and understanding, which is a wonderful applications to train people. So at some point you will probably also see that machines come with a digital twin in order to train people to use it. But the really cool part is testing and simulating scenarios. So you can try all kinds of things that you wouldn't want to try on the real thing, but that you can safely try on the virtual thing. And I think in the presentation before, we also saw that people are using simulated environments. And I think that also connects to this kind of things. Now, if we then look at what a digital twin is in terms of system parts, the central element in a digital twin is the database. And database in this term is a very broad concept because it also includes the model data and also the model itself, sort of. As I said, the digital twin starts in the design phase, where you have the drawings and the specifications, all kinds of metadata, and lives through the build phase, where you collect production data, and then you move into the operation. And then you start collecting sensor data. What people often forget is that sensor data is only part of the things that you want to collect. You also want to collect all kinds of use context data. For instance, for many applications, and I think also for water distribution, things like ambient temperature are important, or rainfall, stuff like that. It also is relevant if you want to study how your device operates. And then, of course, people expect these days a very nice user interface, preferably a 3D graphics interface, where they can browse through the data and request all sorts of additional data and analysis, stuff like that. But for a company like Fortec, I mean, building these kinds of systems is what we do, but the real fun part is in the algorithms. And the algorithms can be a wide range of things. And in the second half of my talk, I will be discussing a couple of examples. One thing to notice here is that I also put an arrow between the model and the algorithm. And that is intentional because many of the AI algorithms or approaches find it hard to incorporate the physics of what you are doing. And our experience is that a model can be used together with artificial intelligence to also include the physics and come up with a better answer. And I'll show you an example later on. So this is a digital twin in its full form. And now I would like to concentrate on a few examples of algorithms that we have been using on, have been working on, and that may be useful also in the context of water distribution and water management in general. So the first thing that I would like to discuss is a form of anomaly detection. And this comes from a different field, actually, from traffic sensors. But I think the way we handle this carries over also to other kinds of sensors. So I thought it might be interesting to discuss this. Traffic sensors are the sensors that are located along the highways and also the smaller roads. And they collect data about passing cars, about the speed of cars, the intensity of cars. And there are quite a lot of these kind of sensors in the order of, I think it's some 10,000 of these. And you can imagine, I mean, they are devices. So from time to time, one of these sensors breaks down and starts to collect the wrong information. And we were asked by the owner of these sensors to come up with an algorithm to automatically detect the sensors that are suspicious. So we approach this in the way that you do that if you are going to use machine learning. So the first step that you take is you define the features. Features are is the form of the data that you expect is going to be indicative of the errors or the problems that you expect to find. So the features that we collected are the statistics of the traffic data, also the relative values between neighboring sensors, and also sorts of context data like the weekday, the month day, whether it's a holiday or not. And altogether, in the end, we had some 100 features, I would say. So 100 data items per sensor per time step that might have some information about whether the sensor works properly or not. Well, and then we did the right thing, of course, a good scaling and a principal component analysis to remove any correlations that may hamper the development. And then we applied several machine learning algorithms to see which one works best. A couple of supervised methods, but problem there was that we had very limited label data. So we had very little examples of actual faulty sensors. I mean, there are a lot of those, but it's not, this kind of data is not collected on a structural level. So most of the work that we did was in unsupervised approaches, which are basically forms of clustering algorithms. And it turns out that these clustering algorithms are very well suitable for detecting suspicious sensors. So in the end, we had an algorithm and we ran it over a very large data set. And then we came up with a couple of hundred suspicious sensors in this data set. And we put it before the experts. And then, of course, there were quite a lot of sensors from which they said, yeah, well, I would have seen that if you would have asked me. But there were also quite a lot of sensors where the experts said, well, I don't see what's wrong with it. And then we said, well, our algorithm suspects that this is suspicious. And then on the second look, the experts actually said, yeah, you are right. I wouldn't not have noticed that, but this cannot be right. So this is a nice example of how an algorithm can help operational people in detecting faulty sensors. I don't think it's rocket science. I think everybody with a background in machine learning could have done this, but it's a nice example of how you can use these techniques in an operational setting. The second example that I would like to give, and this goes more into the water distribution field, and that is not originally work from Vortec. It's work by Johan Vitier from Vitens, who did a wonderful job, I think. So I'm explaining more or less his work and also the things that we added and did to build on that. So the principle of leakage detection is rather simple. You make a prediction of the expected demand and the uncertainty therein. And then if you have your actual demand measurement, you can see whether it matches the expected demand, and if not, then there could be a leakage. It's as simple as that, but of course there are a couple of issues there. First of all, you have to predict the expected consumption. And in the original form that we started on was a use of an explicit combination of trends. And that's worked remarkably well, I would say. We tried, or actually one of the students that did their internship at Vortec, actually one from Eindhoven, try to do this prediction also with a convolutional neural network, CNN. She used the WaveNet package for that, and I think WaveNet was not designed for this kind of application, but it works quite nicely. And she found that the CNN, the convolutional neural network, does more or less the same as the original one, which was already quite good. Then if you have the prediction of your demands, then, as I said, the observed minus the predicted demand gives you an indication of whether there is a leakage. And what we also added is a couple of very simple checks to sort out whether it's actually a leak or not. One thing that could happen is that the demand in one DMA, district metered area, is large, and in the neighboring one it's smaller. And then that indicates that there's some delivery going through the DMA that's not properly measured. But that's not a leakage. So by looking at neighboring DMAs, you can sort out these kinds of non-leakage events. And another thing that we added was that you can also look across many DMAs, and if you see a high demand in all the DMAs, then it's probably not a leakage because it couldn't be leaking in all the DMAs at the same moment. Very simple, but it works nicely. This student that did her internship at us also tried to use the CNN, the convolutional neural network, for classification. So classifying a data point as being a leakage or not. But it turns out that it's not as reliable as simply the very simple checks. So summarizing, the advanced stuff like CNNs do work for demand forecasting, but I think that was already known. And for classifying a leakage or not, very simple methods can be enough. Then, once you have you know that there's a leakage somewhere in your system, then of course it's also important to know where this leakage is. And for that we use a combination of a traditional model, in this case an APANET model, with data. So if we have a well calibrated model, then if the observations start to deviate, you can sort of use this model to back compute, if you like, where the leakage is probably going to be. And initially we used a very advanced methods from the OpenAI data assimilation framework, which uses a very sophisticated optimization algorithm. But it's turned out to be far easier to have a very simple search algorithm where you simply put a leakage somewhere in the model and see what the effects are in the observation points. And if you made a leakage in your model at a location, at the right location, then you might hope that the signal in the observation points matches this. Well, we found that with all the caveats there are, and I think you can imagine quite a few of them, it works remarkably well. We did initially a lot of experiments with a virtual or with a simulated environment, and there we could very well localize leakages. And now, the past year, we've been starting to work with real field data. And also there, the initial results are quite promising in that we can, in many cases, find a leakage within 100 meters of the actual leakage, depending on many things, but it works surprisingly well. And at this moment, we are studying the sensitivity because you can imagine that all kinds of disturbances in the system are probably going to hamper the accuracy. And that is what we are studying together with people from Deltares. Now, this is a few of the examples of the kind of algorithms that could be used in a digital twin setting or in an IT system in general. There's one last slide that I want to show, and that is, and I think I already hinted at it at the beginning of my talk, that a machine learning of AI algorithm is not a standalone thing. It's actually part of a chain of things that you need to do. And there's a wonderful book which I recommend for everybody by Andrew Murkoff, Machine Learning Engineering. And that sort of describes all the steps you take before you get an actual AI up and running. And what is important is that you always start out with a business formulation, a business question. When we first moved into the field of AI some 5-6 years ago, many of our customers came to us and said, well, I have a lot of data. Can you do some nice trick with that? And very soon we found out that that is not the way to go. So you have to approach it from the other side. It has to start with something that you actually need or that the business needs. And you have to have a very well-defined goal. I just described this example of the detecting faulty sensor data. There was a very clear business goal there because detecting faulty sensors is at this moment very labor intensive. And if you can automate that, that is good. If you have that, then you can start your data collection and preparation for data that matches whatever you're trying to do. And you do the feature engineering and the model training. And then you have a model and you evaluate it. And these are the steps that are usually taken in an AI project. But then it gets interesting because then you move into the deployment phase. And that means that you have a model in operation and you get the entire maintenance question of operational systems along with it. So you have to keep track of how the model functions. Typically, an AI model at some point deteriorates, and you have to detect that in time. You have to modify the model in time, doing a retraining or actually developing a new model, and also take that into production. And I think for operational applications, it's important that an AI is more than just the algorithm. It's also the entire system around it. So that brings me to the end of my talk. I'm not quite sure whether I did not take too much time, but yeah, there's some room for some questions.
All right. Thank you, Mark, for this interesting talk. Yeah, you spent a little bit more time than expected, but
sorry.
Maybe we'll come back in the general discussion. People, when they have questions related to your presentation, then they will definitely come back. But I would like to continue with our last speaker, which is Caspar Gelen. And Caspar obtained his master degree in biotechnology and bioinformatics at the Wageningen University. And then some 4 years ago, he started his PhD project at the Mathematical and Statistical Methods Group, also in Wageningen. But he has his desk here at Wetsus in Leeuwarden, with his focus on drinking water networks. And his project is positioned within the one of the Wetsus themes on smart water grids. And in his research project, he integrates machine learning, statistics, and system theory. And with the aim to detect or even prevent leakages. Well, I would say we are eager to hear more about this. So, Caspar, your turn.
Thank you, Karel. So I hope to tell you something in my presentation about what research I'm doing in my PhD at Wetsus and Wageningen University. I'm in the last year of my PhD, so I've already done quite some research, and I hope to give you a tour of what I've been working on in these 4 years. So it's a smart water grids team that I do my research in, as mentioned by Karel, where we look, where my part at least is that I look at water distribution systems, drinking water distribution systems for fall detection and isolation. So are there leakages happening? Can we prevent these or detect these? So that also has some overlap with what Dr. Roest already told us in his presentation. Can we come up with a mitigation strategy? Can we build an algorithm that can easily detect, for example, leakages and convert this in easy to use early warning and decision support tools, so that we in the end get improved management of our drinking water grids. To back up a little bit, there are basically 2 different approaches to obtain more insight in what's happening in your drinking water distribution network. We have the equipment-based technologies, ultrasonic inline inspection, for example, with robots that crawl through the pipes and using ultrasonics can in a high resolution map every millimeter of the pipe to see what the condition is, or even smart pipes that come already on the market with that are delivered with sensors already embedded in them. So you just install a pipe that automatically measures the stuff. Also a nice example of a very capable sensor would probably be the example mentioned by Professor Baltus of these Smarbles. That would also be a very interesting sensor tool. So these would be equipment-based technologies that give you high resolution of data, mostly about a small section of your network. However, what I focus on is more a model-based technology. So it's closer to what Dr. Roest was also talking about. I look at what is already coming in. I unfortunately do not know how to make a Smarble myself, but luckily there are already a lot of sensors installed in drinking water distribution systems, flow and pressure sensors, as I show here as the green symbols in this schematic water distribution network. And from these sensors we can also obtain measurements from which we can say something about the entire network or large sections of the network. So what is exactly measured in a drinking water distribution network? Maybe already it was shown in an example by Dr. Roest, but I will recoup it here. We have flow and pressure sensors, and if we for now focus on the flow sensor, we see that we have a pattern that looks a lot like we expect the traffic to be. So at night there's a low flow because there's a low water demand by the end users, the consumers. People are asleep, they're not showering, they're not drinking a lot of water. But when everyone gets up in the morning and when everyone gets back from work, then we see the rush hour. We measure higher flows through the conduits, through the pipes in the system, due to the large consumption of water. So that's the kind of data we're dealing with. We get measurements of flow and pressure in the network. As also already mentioned by Dr. Roest, we can use this data to build a prediction. So the VTENS dynamic bandwidth monitor that was discussed is an example of a method that tries to predict the current and 1 week ahead future water demand based on what we have seen in the past. So we get real-time data, so in real time we can make a water demand forecast and we can look at the deviations which might indicate that a burst has happened. In this example we see indeed a higher flow than expected because there was a pipe that burst, so a lot of water left the network. So we measure a higher water transport flow compared to what we expect that the people actually need, which indicates a burst. But you want to make sure that this is indeed a burst. And that's the important part here. So I will quickly recap what this technology does. If we have in blue our measured water demands, we can look at a certain time point right now in real time. Let's say it's 12 o'clock. We can take this point, but we can also take exactly 1 week ago on the same weekday, the water demand at 12 o'clock, and we can do this, let's say 18 weeks back. And if we draw a line through all these points, then we get a nice prediction in orange of what our water demand will be in the following week. So based on historical sensor data, you can build a very nice prediction, which is also what this dynamic bandwidth monitor that was discussed does to predict the water demand. And if we look at how this performs, we see that these kinds of methods work quite well. They are very strong at predicting the regular water demand. So in orange, the prediction 1 week ahead. In blue, we have the actual data. We're now looking at December of 2018 of the measurements. So it's very good at predicting this when the data is regular. However, Christmas is coming up in a few days, and we will see that there is a deviating pattern right now during Christmas. However, it was not Christmas a week ago. So that's something that you need to compensate for, else there will be triggered now a burst alarm, but that will be a false positive. There's not actually a burst happening. It's just a holiday where people use water in different amounts and at different times. So this method is quite strong at the regular water consumption, but this method struggles a little bit dealing with deviations from this regular, so non-seasonal events as we call them. And Christmas is one you might see coming, but how will a pandemic affect the water demand? Or maybe with certain weather conditions, people use water in a different way. So there are a lot of factors influencing this, and they all influence us in a different amount. One way to solve this, as was mentioned for this dynamic bandwidth monitor, is to implement checks. If people suddenly use more water in every spot in the network, then it's probably due to, for example, a holiday, and it's not actually leakage, because the entire network hopefully is not leaking everywhere at once. However, I also try to tackle this in a different way. So the questions here are which factors do influence our water demand in, for example, our sensor A, and how do these factors influence the water demand? Instead of trying to identify all these factors and trying to implement checks that then correct for these factors, and also instead of looking what the extent is towards which these factors influence it, we can look at the other sensors in the network. So for example, I take Christmas as an example here, but it will work for all factors. If we have a false alarm, we have a deviation in this prediction due to Christmas. Well, it's also Christmas in every other spot in the network. So instead of building a check, what we can actually do is we can predict our water demand by looking at what's happening around the sensor. So instead of looking at the historical data of a single sensor, we can use what's happening right now at every other sensor to automatically correct and take into account these different processes without even having to identify what is actually causing this deviation. So we do not predict one way ahead. We look right now at what the other sensors are doing in order to suppress all these false positives and only trigger an alarm when a real burst has happened. I will try to explain how this works in some detail. I hope this will be clear. So I zoom in a little bit in my example network. I'm trying to predict the red sensor over here. I'm doing this using ridge regression. What that basically means is I take all the other sensors around the sensor of interest. They're shown with the different colored heads. We see in gray that they measure in the last few days a certain pattern of flow or pressure, for example. And we can multiply all these different sensors with a certain factor to then fit what's happening actually in this red sensor. And we multiply with these P factors in order to come up with the best fit. So this we do for the past few days. We also make sure that it uses all these different sensors to some extent. So it will not only fit on one sensor, which is a ridge regression or Tikhonov regularization that we apply. And we remove outliers. If you see, the red square indicates where a weird anomaly is happening in my purple sensor. So from the training data, we ignore these different measurements in order to make sure we have the best fit and reliably fit all the sensors. And in the end, we can then make a prediction for what's happening right now, a nowcast as we call it, not a forecast, a nowcast of the measurements. So to go to some results, which might be a bit more indicative, a bit more illustrative of what's happening. I show here twice the same blue measured data of June in 2017. In blue, we see the actual measured water demand in the sensors. Then in green, in the bottom graph, we show the prediction with traditional methods, such as this dynamic bandwidth monitor, focusing on past measurements. In orange, we show this exogenous water demand nowcasting, so based on the other sensors around my sensor of interest in the network. There are two leakages that have occurred at this time. This is a data set from VTENS. there were two pipes that burst, causing a deviation in flow. We see that especially this exogenous newly developed method is quite certain and quite strong in detecting these deviations. The traditional method is also capable to some extent in finding these deviations, but struggles from a lot more false positive. If you look at how well the green line matches the blue, we see in a lot of places that this is not the case. So we'll have a lot of false alarms, and you won't be able to see maybe to be certain that which of these alarms is actually a burst and which is a false positive. Where the top exogenous method shows more capacity to fit all these factors, social demographic factors that have an influence on the water demand, while still retaining its capacity to detect bursts and having a way lower false positive rate. So that was an alternative method of detecting bursts that I developed. So we don't need to look what's happening, what's the weather, what holiday is it, or is there a pandemic going on, and we do not need to know the extent towards which these factors influence the water demand, because the extent is already captured by the other sensors that then gives us this approach. In theory, we have a beautiful network with a lot of sensors. However, sensors are costly, and also to make sure that all the data that these sensors collect is correctly coming to us is also costly. So in reality, it looks a little bit more like this. We have the key points in our network we've censored, especially to create these DMAs, district metering areas, sections of the network where we exactly know what's coming in, and thus can also compare with what's going out. However, it is important to make sure that we have as much information as possible with a limited amount of sensors. So optimal sensor placement is a very important theme also to consider. Network sensitivity analysis is a strong approach that can be done. I think this is also what Dr. Roest illustrated in his second to last example. If you have a digital twin, if you have a hydraulic model of your network, and if this model is very accurate, you could simulate a virtual leak. So in your model, you simulate the leak at this lightning bolt location, and then you can see where in your model do I see a different flow, do I see a different pressure as a consequence of this leakage. So that's the yellow illustrated area over here. We can do this for multiple locations. So if we simulate a virtual burst in our model in a different location, again, we get an estimate of where we will be able to detect this leakage. And then those places in the network that are able to find the most leakages from the most different locations would be ideal sensor locations. Because if you place a sensor here, you would be able to see both these theoretical leakages that I show you. So that's a way of determining where to place a sensor. They started developing this in '98, and even recently people have been working with this because it's still a very strong technique that will become better and better. The more you work on your digital twin, the better your hydraulic model gets. Dr. Roest had an example. I also included here an example of KWR from last year, where they also worked on a technique that works with this methodology. However, I also try to tackle this problem, but I will tackle it from a different approach. I will use systems theory, a field of mathematics, and observability functions to also try to identify where placing a sensor would give you the most information about what's happening in your network, so that you most accurately can monitor what's happening in your network. The dynamics will be included in this model, so it will include all the hydraulics that are happening, even the pressure wave velocity, which is usually not included in these kind of models. No simulation is required. No virtual leakages have to simulate it for each different locations in the network. It will solely rely on the properties of the network itself, and it will be constructed in such a way so that it can read the APANET models and is completely open source. I will keep this brief, but I will hope to show you how this works. So we look at our model. On the right, I show a very simple schematic model with two reservoirs, a pump, and some junctions of pipes and some pipes, where the head pressure H and the flows Q. That's of course what's happening in the network. So those are your states. The flows and the pressures in your network are your states. The outputs Y, those are the sensor locations. Those are the places that you can measure what's happening in your network. All the hydraulics and dynamics are captured in matrix A. And we have our sensor locations that are also in matrix C. Usually you either look solely at matrix C, where are our sensors and how does this affect how much we know about the network. Or you try to simulate your model with the assumption that you already have a very strong model and that the results you get are very accurate if you simulate these bursts. But you can also just look at the properties of your network. So that would be these two matrices. And with observability functions, we can, from this method, also come up with a way to determine where a sensor would give us the most information that we need for our network. This works by, per possible sensor configuration, calculate the sensor placement energy, and then find that spot with the highest sensor placement energy, thus the highest yield of additional information by placement of a sensor at that location. If I show you this example on the right, I can color this then with this methodology to show you that the green junctions are in this theoretical small example are the optimal locations to place a sensor, while the yellow to red locations would be less optimal. And these kind of techniques can be rolled for networks of any size. I again show you here a smaller one. Currently, I can also do this sequential sensor placement, and the next step will be to do this for multiple sensors at once to determine where do I want my sensors. So I will leave you with a small example. We see a network here with a blue water inlet, and I will add pink sensor locations to the network until we have a very observable network where we know everything that's happening. And that will look something like this. So we can iteratively, sequentially place sensors in this network, and you will see that it will become more green. So we'll have more information about what's happening. And with that, I would like to conclude my presentation, summing up here the advantages of this method compared to the currently employed method and compared to this sensitivity analysis method. And I hope to have given you a nice insight in the research that I've been conducting.
Oh. Thank you, Casper, for this presentation. Looking at Dukle, we have some questions.
Yeah. We don't have any questions at the moment, so please feel free to still ask your questions. In the meantime, I have a question for Caspar, and it would be how many sensors per DMA kind of estimate would you need to apply this method reliably?
To use this exogenous nowcasting method, of course, more sensors will be better. I also try to do this for as limited number of sensors as possible. You need some sensors in your DMA that are not already used to calculate the water balance of your DMA. So you would need, let's say, 2 or 3 sensors at a bare minimum that are incorporated in your DMA, can be either pressure or flow, that are not used to calculate the water balance. And that already gives you quite sharp results with this exogenous nowcasting method. If you do not have a high number of sensors, you can always run the method next to the traditional based on historical measurements method, like the dynamic bandwidth monitor. And as soon as more sensors are incorporated, then hopefully it will become clear that this is a very strong method to reduce the false positive rate.
All right, thank you very much. There's one more question, and it's a question of asking Caspar, what do you mean by energy in the slide optimal sensor placement?
This energy comes from some observability functions, as they're called. So we look at some mathematical functions that basically try to maximize the information gain, the information you achieve from placing a sensor at a certain spot. And that's based on the concept of observability, if you would like to know more about this kind of calculations.
So it's a bit more like entropy, perhaps?
Entropy would be another great term to use, yeah.
Right. No further questions at the moment.
Yeah. Well, then the floor is open for the general discussion. So please come up with questions. I have a question here, but let's first see whether there are questions from the audience.
We can actually start with an interesting question for the first presentation, and it would be from Joost van Summeren. How would you retrieve the smart balls after use?
Yes, that's a really good question, and a non-trivial one, like we discovered. So we in the setup in the lab, it's relatively easy. We have a sort of a sieve attached to a handle, and we just can sieve the balls out and pull them up, and that works quite well. In some applications, like for example mixing tanks, we can do this in a somewhat similar way. But we found that in other applications, we actually sometimes lose these marbles and we can't find them back anymore. So retrieval is still high on the list of things that we need to improve, because, for example, for water pipe systems, we definitely do not want to lose these sensors and have them drift inside a drinking water system. That seems like a pretty bad idea, considering the chemicals that are in batteries and stuff like that. So that is partially solved, but it's still something that has a lot of attention. And also, for example, if you have pipes that are under high pressure, then it becomes also more complicated to get these balls in and out in an easy way. So more work to be done there. It's a very good point.
It's understandable. I think. Thanks very much for your answer. And the question of Steen Jacobsen to Mark, would it be? Could you elaborate a bit on the subject goal definition with some good practical advices or framework? Mark, I hope you know what this question is exactly about.
Yes, I think I do, and I think it's a very good question. The way we approach this in many cases is that you first look at what is going on at the customer, who are the stakeholders who are doing things, and what is hindering them, what is taking too much time, or what is too costly or inaccurate, and stuff like that. So you find ways actually to start helping people, and that is the start for defining goals. If you find someone in the company that could be helped with AI, then the next step is to see if AI might actually help. So do you have the right data to help him or her? And do you expect that an algorithm can be developed? And how much benefit would it give? And then you have sort of a business case for what you're trying to do. And only then you start working on your actual project. So it all starts with finding good things to do to help people in their operation. I hope that answers the question.
I think it does. I think it does. And another question to Kaspar. What is the most accurate method? What would result in the most accurate method? The flow or the pressure measurement? Could you comment a bit on that?
Flow measurements are usually more interesting to look at, or they contain more information, I should say, since they really contain this regularity of the consumer water demand, let's say, the real consumption, which is this regular pattern. A single human is highly unpredictable, but in large groups, apparently, we're quite predictable. And that regularity, of course, strengthens a lot these methodologies. However, since you rely on these indirect sensors just for suppressing all these exogenous factors that are exogenous processes that are going on. Pressure data could be seen as a bonus. You could also use the pressure sensors in the network to supply this information, because if a deviation happens, then this is usually also seen in the pressure data, because pressure and flow, they have a relationship with each other. So therefore, it's an additional source of data that you're not solely looking at your flow sensors, which is usually the case for DMA water balances. But in this case, we can also incorporate our pressure sensors. So it's more of an additional source of information you're using. But the flow data remains the backbone, let's say, of these kind of methodologies.
Is it also because you think the pressure should be kind of equal in the whole system? The amount of information is not too much there?
Ideally, of course, the pressure is maintained so that everyone has a nice steady stream of water from the tap. So especially in big cities where the networks are more mazed, as they call, there are more loops in the network, you see that there's a really regular pressure everywhere. So that would be less helpful indeed. However, deviations usually will still disrupt this very regular pattern. Since we're talking about leakages, you will see spikes in a maybe normally quite steady, flat pressure measurement. So there's still a lot of information in there, independent on if the pressure has a regular pattern during the day, let's say.
All right, interesting. Then a question to Um, about the sensors. So could you make the sensors magnetic? I think maybe Jurg, if you can explain a bit more, why would you why would you like that? And in the meantime, we could answer the question to Professor Baltus, of course.
Okay, sorry. Yes, so we could make them magnetic, but I'm trying to think now what the purpose would be. I could imagine that if we would put in permanent magnets, then we could make the sensors attached to the wall of pipes that would be of material that would be attracted by magnets. We have been thinking about doing that if we could have an actuator that would release the sensor again at a specified point in time. And we have been looking at electromagnets for measuring distances. And that part actually works. The permanent magnets, I'm not sure. So the question is, for me, which of these two, or maybe even a third option was the question imagining or targeting?
That makes sense. And sorry, did you want to say something? Okay. Kaspar, again, could the algorithm for leakages also work with smart meters at households instead of sensors only in the drinking water pipes from Roel Diemel?
Yeah, I've heard this question before. That's of course also a very interesting field and a new development that these smart sensors become more and more available, or is more and more research being done to those. Yes, in theory they could. If they just measure what a single household is using as water, they can already be used to get a better estimate of what will be the water demand per household, let's say, or the water demand for certain sections of the network. So it will definitely improve any hydraulic model or any digital twin of the network you have as a bare minimum. It will be very helpful there. And second, there's also being looked at if the sensors can also measure pressure. And if you can measure pressure there, then you really have a sensor that you can directly use in this optimal sensor placement technology. So this is definitely a very interesting new data source that potentially could improve these methods a lot. Yes.
So a lot of options to improve the models with the smart meters. Sounds very interesting. A question for Mark again. Is your method suitable for sewer systems?
Yes, it is. And in fact, we tried that with a very short project. But the approach that we took for detecting leakages also works for sewer systems. There are differences, of course, because a sewer system is only partially filled most of the time. And we use a somewhat different method there, but we were capable of identifying disturbances, like things that are in the sewer that are not supposed to be there. It was a very limited experiment, but it was quite successful. Would be interesting to try it again on a more elaborate scale at one point.
Okay, thanks. And Caspar again, you already explained that you need a certain amount of sensors per DMA, but of course then the size of DMAs are differing. So could you say also kind of an estimation of amount sensors per kilometer, or is that a bit?
No, I could not, but I could share another more insight in this question. For a sensor in this exogenous method, it's more important that the number of consumers, let's say, per sensor is a very important parameter. If you have a sensor that supplies a lot of consumers, ideally human consumers, not industry, let's say, because again, this regularity, then that is a really strong source. So you can use a lot of sources, and also industrial sensors in industrial areas are very important. But it's more important that you have quite some number, or that you try to maximize number of consumers per sensor, let's say, where the sensor is in a network, than it really is to have a certain number of sensors per kilometer. That's not something you really need to take into account. What plays a role is we assume that a burst is a quite local event. that to some extent can be seen in different parts of the network. But if you look at the other sensors, you ideally don't want those to detect the burst because that makes it more easy to really find back this burst as only happening on that location. So you have some localization in there partly. And therefore, it is important that you, a larger DMA is not a disadvantage, let's say. You do not need the smallest, most well-censored DMAs for this to work. Larger DMAs might even be more suitable.
All right. And a question again to Peter Baltus. Are there any concrete plans already to employ the smartables in a real application on a short notice?
Yeah, so on the on the smartable side of things, the Antea, the company that we're working with for the industrialization, they are doing experiments with some organizations to try this. For currently, they're ongoing experiments with mixing tanks and with sewer systems, and so that is getting closer to reality. It depends a lot on the application. For some applications, the requirements are just easier to meet with the current technology than for others. So my expectation is that we will see not all applications becoming feasible and addressed at the same time, but probably the easier ones first, and the more difficult ones will take more time and further technology development. But yes, there are experiments going on, and they already give interesting data. So it looks like this is, much closer than for usual research projects that we would have at the university.
Oh, that's interesting. And did you consider also other parameters like pH, oxygen demand, and perhaps other parameters? Because I know the sensors are not so easy to get very small. Do you have any vision on that?
Yes. So at the moment, we just took the sensors. So for these balls, the sensors that were available off the shelf. And of course, we didn't have a very strict size limit, right? So that gives us some flexibility. If we go smaller, then we have two problems. One is indeed the size of the sensors themselves, but there is in the world quite a lot of work on miniaturizing all kinds of sensors. And sometimes you can get the same information through different sensors or through different combinations of sensors. So that's also something that we've been looking at, and how far that we, to what extent that we can use the evolutionary algorithms that we have to detect the information we want without necessarily having the optimized sensor for that. So that seems like there's possibilities there. In the end, there's also the practical side. If you have sensors, some sensors, they can be easily inside the shell, and that gives us more possibilities to work with diverse types of sensors. But sensors that need to be in contact with the fluid, they give their own problems, right? Because then you need to expose them to the outside without having the risk that they get damaged and without having the risk that they will contaminate the environment in some cases. So the answer is not the simple yes or no. We are looking at more sensors. There are possibilities there, but there are also complications, especially when you want to go small, and especially when you want to have sensors that need to be in contact with the fluid.
Yeah, very clear, very clear. And then again, one to Mark Roest about bandwidth. CNN models need to learn the pattern, so probably need a lot of training data. And might a Gaussian process be easier to fit and equally effective? Could you comment on that, Mark?
Yeah, that's a very fascinating question. I think in general, you are quite right that a Gaussian approach might be more useful. Definitely, because you need not as much data. On the other hand, and in this case, you are predicting a time series, and you have quite a lot of data points in your time series. So the amount of data is probably not an issue here. But I do agree that neural networks, they are very cool, but they always require quite a lot of data. And in practice, we see that many of our customers don't have the right data or not the right amount of data to use them. And then you go to other sorts of algorithms. And in fact, much of the algorithms that we use are really very simple, as I explained, clustering types of algorithms or simple regression type of algorithms that don't require as much data. But I do agree that the Gaussian approach might be better in this case.
All right, all right. And one more question from my colleague, Karel Keesman. I would like to
Yeah.
first question.
Well, maybe I can ask this question I would say to all of the three presenters. What do you see as the biggest challenge for applying AI in water technology? Could you, let's say, within 1-2 minutes, respond to that? So I would like to, well, maybe I'll start with Peter, just in that order.
Okay.
And then Mark, and then Caspar at the end.
I think, as far as we can see, the challenge is in the combination of making the right choices from the large variety of AI subdisciplines and algorithms that are available for specific applications, and that in combination with the challenge of making it practical. Right? We see that especially towards now that we're getting closer to more industrialized applications. There are a whole lot of practical things to deal with, like, for example, if you have algorithms that require lots of data and you need lots of sensors, how do you get all these things to be charged with 2 batteries at the same time and start at the same time and have a registered time moment when they enter the system? There's a lot of these practical things that we need to solve, and they interact with the choices for the algorithms that we make. Because if you can do this with 2 or 3 sensors, then life is easy. If you need 3,000, then either you need more technology to deal with these things, or you need a whole class of students to help you.
Right. Thank you. And Mark, can you respond to that?
Yeah, sure. I think I fully agree with Peter. Perhaps I would phrase it a bit differently. My feeling from what I've seen is that getting the AI and basically the entire data infrastructure is probably an important issue. I mean, water companies have an IT infrastructure that has been going for a long time, and the demands are changing. I know they are working on improving that and getting ready for the AI part. But you also have your legacy in terms of IT systems. So I think that's a challenge. And also a general challenge for many users of AI is the acceptance by the end users. People tend to think, I've done this for many years, I know what I'm doing, so an algorithm cannot possibly do it as good as I can. So there's typically a lot of resistance. I'm not quite sure whether that also applies in the water sector, but it is a very general problem. But I would say the IT infrastructure and getting it all working and getting the data flowing, that is probably an important issue.
Right, thank you. And then last one, Casper, please.
Yes, I think the points just made by Dr. Roest, I agree with those. I think it will be important that all the different techniques that are being developed are combined. Because digital twin, as explained, requires everything to be, every part of the process of the water distribution grid to be known and to be modeled in real time. So, for example, you need more sensors, but you also need very accurate information about your infrastructure. So maybe techniques like the smarbles or like the ultrasonic inline inspection, where they're now used to just map a single pipe or trajectory to find out what is the condition of this pipe. In the future, maybe you can also use this to update your model to get high accuracy information about the state of the asset, not only for replacement strategies, but also for improving your hydraulic model, improving your digital twin. And then if you keep improving all these information sources and keep combining them together, that will in the end result in the strongest predictions and the strongest outcome of all the algorithms you apply. So that you indeed do have enough data to start doing supervised learning, where maybe now the data is not accurate enough, or you don't have enough labels, and it's a lot of unsupervised work, as I've also noticed. I think that those are important challenges that are still there, but interesting challenges that also I see being solved in the coming years.
All right, thank you.
Thank you, indeed. And Caspar, one last question. I think this last question for the energy optimization. Generally, you solve an optimization problem, and the hydraulic constraint is non-convex. I don't actually know what the question means, but probably you know this.
Ooh, that's a tough question indeed. Of course, the model that you have there should be stable. So you should have an accurate model, but also a stable model in order to do these kind of calculations. For the case of hydraulic distribution, water distribution, drinking water networks, usually you end up with a stable network. I've not encountered this problem as such, so these observability functions could always have been applied because the examples that I've looked at also from real-world networks all were suitable to apply this technology. I hope that answers the question sufficiently.
Yeah, I hope so too. At the moment, I think we're out of questions almost. There's one last question I would like to ask Peter Baltus, the linear correlation between delta t in the time of flight and distance. Is it observed when the sound travels a 90 degrees corner?
No. Then strange things happen indeed. But 90-degree corners are nice because we can detect them in other ways, right? Because and these corners, these sensors tend to hit the wall. They don't nicely flow in the center anymore. And we can detect that using the accelerometers when that happens. And so we know when these things happen, and we can then later filter out these data points. So that is something that can be solved. But indeed, in corners, we see sometimes strange outliers, and you can filter them, for example, in this way. Also, if you have, for example, a T-junction, you get strong reflections from the back wall of the T-junction, and you get then multiple echoes. So there are situations where you get wrong readings. And the easy solution is to just discard them, to detect them and discard them. Solving it is much more difficult and usually not necessary.
Yeah, thanks for your answer. I would like to switch now to Karel Keesman again to end this session.
All right, so I would like to thank the speakers for this afternoon, for this Wetsus webinar on AI in water technology. This session is recorded and will become available after 1 or 2 weeks or so. Yeah, so we will let you know. So once more, thanks to the speakers, but I would also like to thank the audience for their contributions in the discussion and all their questions. So thank you all, and wish you good luck. Thanks.